For lesson 2.5's Ready, Set, Go, we are working through different types of quadratics. And one thing that we can do is we can refresh our memory that a quadratic can be written as ax squared plus bx plus c. And sometimes that'll be f of x equals, or sometimes it'll be y equals. For right now, we'll just say y equals. For the ready portion, we need to be reminded that the highest degree we can have, and we need to have, is an x squared. So if we don't have an x squared in there, no good. So for number 1, I see it, and there's nothing to combine any like terms with it. So we know that, yes, this is a quadratic. I'm going to leave the justifications to you as a way of practicing that, but just know that it has to have an x squared. For number 3, it doesn't have an x squared, so we might think initially, nope, this is not a quadratic. However, if we take and we distribute this x in, x times 4x is 4x squared, x times negative 5 is negative 5x, and there's nothing else to combine, so yes, this is quadratic. Number 5, 2 to the power of x. Well, I might think like, yeah, that's a quadratic because there's an exponent in there. Well, the problem is that I need this to be an x squared, not a 2 to the x power. Therefore, no, this is not quadratic. For the set portion of this, we are trying to get our equation from standard form into vertex form, and then graph those key elements. So for right now, we can scribble out the c value, that end value. We'll take half of our b term. So we know that we've got negative 4. Take half of that, would be negative 2. So we can put y equals x minus 2 squared. And what I really should have is 4. But what I actually have is 1. So to get 4 down to 1, I would need to subtract 3. Because when I multiply this out, when I complete that square and actually multiply it all out, I have 4 blocks, but my problem only gives me 1 block. Something to keep in mind. So now I have everything that I need in order to graph it correctly. And I'll just go here, and here. Now based on this, I know that my vertex is 2, negative 3. Okay, looking at it in here, what makes it 0? What's left over? And I'm good with my vertex. So we can plot our vertex at 2, negative 3. And now it's a matter of creating a table and seeing what goes in there. I know that 2 is my vertex. 2, negative 3. So I'm going to try to create a couple more points that should help me out a little bit. So let me go 1 to the left of it and 1 to the right of it. If I go 1 to the left, that's the x value of 1. When I plug it in to my equation, 1 minus 2 squared minus 3. So we end up with negative 2. And if I plug in 3, we end up with Got ahead of myself there. Something seemed off. Three minus 2. There we go. Minus 3. 1 squared minus 3, which is also negative 2. So I'd be able to plot those points as well. And just for good measure, I'll do one more. Your job is to show 3 accurate points. So you're going to need to continue this table, but just for the sake of showing you one more, 2 squared minus 3, 4 minus 3 is positive 1. So we would go here. What you'll end up seeing is that, that's kind of gross. Hold on. It would go up somewhere like this. And the big things that I'm looking for are it's pointing up, vertex is here, axis of symmetry is here, being able to identify parts of the graph. For number 11, it's hard because I didn't require you to do 9 and 10, but which of them look wider than the others? And what we should be able to recognize is that the only thing that makes a graph wider or skinnier is what is the A value. And in this case, the A value for 10 is 1/2. For 9, it's 1. If it is skinny, we would have a number larger than 1. If it's wider, it would be a number between 0 and 1. So because of that, we can say that number 10 is wider, and then it's your job to explain why. I would encourage you to graph these, either by doing it through hand, using the vertex form to be able to graph it, or plugging it into a graphing calculator and seeing what it is, but then explaining why. Why is it wider than the others? For numbers 12 through 17, you're just completing the square. Nothing else too crazy. And then writing it in factored form. So it'll be that vertex form in a way. So what we'll do is we will take our b value and cut it in half and then square it. So 7 times 7 is 49, 2 times 2 is 4. So you know that my c term for number 13 is 49 over 4. Writing it in factored form, you would get x plus 7 over 2 squared. Where did you get the 7 over 2? From right here. For number 15, a little bit more of a challenge. 2/3 squared. Well, that's just 2 times 2 over 3 times 3. So you have that, and then your final bit is writing it in factored form, which is right here. I know that fractions seem like a very intimidating piece, but all you're really doing, sorry, I'm off my game here. 2/3 cut in half is 2 over 6, which is actually 1/3 if you simplify it down. Square that, and you end up with 1 over 9. So 1 over 9 is your piece there, and then x plus 2/3 squared would still be your factored. Not really. 1/9 is not. 1/3 is. Okay. Reason for this is we're taking half of our b term and dropping it right into here. Number 17, same process. Half of negative 3/4 would be negative 3/8. Square that, and you get 9 over 64. So 9 over 60. write that a little bit better. 9 over 64, and x minus 3/8 squared would be your factors. For numbers 18 through 21, trying to review a little bit and go back through recursive and explicit equations. If it is linear, writing both, recursive and explicit. If it's geometric, or if it's quadratic, we're only going to write the recursive. So the first thing we need to do is figure out if it's geometric, arithmetic, or what is going on here. So we know plus 3, plus 6, plus 9, plus 12, which means it's not linear. But looking at the second common difference, we know that we have plus 3. So we know that this is quadratic. And the equation, first we need to identify our f of 1, which is 7. So our f of x is going to equal the number right before it, plus our second difference times x, plus our y-intercept. And if you're thinking, like, where would we get the y-intercept from? If you plot the points into Desmos, you can see that it's curving around, and it would end up curving right back to 0, 7. And we'll talk about a regression a little bit later, but you can plot those in, see what happens, and just start to make some inferences of your own about where you think it's going to go. For number 21, similar process. We have 12, 14, 16, and 18, which means that we have a second difference of plus 2. Now, based on the second difference, we know that it is quadratic, has that common second difference, and our recursive equation, f of 1 equals 28, and then f of x equals the number right before it, the output right before it, plus our common second difference times x, plus 18. Why 18? Well, take a look at your differences here. 18, 16, 14, 12. The output right before it would have to be 10 less than this 28. So our 0 term would actually be 18. It's working its way backwards a little bit, but this is kind of a review. I don't know how far we got into recursive equations for quadratics, but this is the correct representation.